Hello, everybody. I want to start by asking you, how many of you are incoming freshmen? So you're in your first week or so of dealing with college. Bet you guys are getting an education already. I'm thinking a lot of you probably weren't thinking a couple of weeks ago you're going to be in a room here at this time talking about how we reverse engineer the human brain and where that all fits into your plans as far as whether you're going to be studying, chemical or mechanical or electrical engineering or what it is, whatever pathway you all may be studying. This much I know, and I think this is really important, and Dr. Tavicoli has already done a good job, I'm sure, queuing up for all of you, the importance of what we do as engineers and where we kind of stand in the scheme of things when it comes to innovation and entrepreneurialism. And as you go through your next several years here at Kettering and work your way through our program, you're going to spend an awful lot of time looking at various aspects of engineering. You're going to be looking at specific details and disciplines, and by the time you get done with this, and by the way, I should have let you know up front that I'm actually an alum from here. I graduated here a long time ago, and a really long time ago. But the best part is some of my professors are actually in the room with us here today, so it's not that terribly long. But I know what you guys are getting ready to embark on, and I have a pretty good sense of what it is you're going to be going through as you go through your next 5 years, and you're going to learn an awful lot about just every aspect of engineering and science and math, and by the time you get done, you're going to probably despise science and math, but you know what, it's great stuff, because at the end of the day, when we break it all down and it comes down to what do engineers do, ladies and gentlemen and incoming freshmen, we are problem solvers. At the end of the day, we figure things out. That's what engineering's really all about. When people don't know the answer to something, we solve the problem. We look for things that are not known, and we don't run from the unknown, we run to it. We look for things that we can figure out, that we can solve. We figure out how to make new knowledge that maybe somebody else has come up with, but we take it, and an engineer is good at making that new knowledge useful. We work problems, we see the parameters, and it doesn't matter what kind of a problem it is. And let's face it, folks, in science and in our world, the world is loaded with problems. We got more than plenty of problems to deal with. But when we see a problem, we typically see all the parameters, we see all those dots, and what engineers do is we figure out how to connect the dots, how to understand the problem, how to unravel its mysteries, and most importantly, how, again, to solve it. In the process of doing that, sometimes we create entirely new things. As you go through your engineering work here at Kettering, you're going to learn about things like, for example, design processes, formal and elegant ways to create something that's maybe completely from scratch. It wasn't even known before. That's creating something entirely new. We take existing things and we figure out ways to improve those things. And if you look in our world today at all the various things that, for example, energy problems that we have, and the work that's going on in finding new and more fuel-efficient vehicles or modes of transportation or different sources of energy, there's nothing new there, folks. I was driving up US 127 north of Lansing the other day, heading up into the northern parts of Michigan, and all of a sudden I'm like, where'd all these windmills come from? And there's just dozens and dozens of windmills suddenly visible from the road. And I don't remember them being there a year ago. Now all of a sudden it's all you see. But you know something? Windmills, nothing new. Last I checked, they've been around a few hundred years, generating electricity with wind, nothing new. Yet it's engineering work of today that's making these kinds of technologies more practical, more usable, so that maybe we are transitioning to a point where we can start effectively and practically getting something from wind energy versus, it's a great idea, but the cost, those kinds of things. We improve existing things. Sometimes, though, and this is the crux of what I want to talk about today, sometimes we create understanding through a process called reverse engineering, where in reverse engineering, we try to figure out how something works many times by taking that something and taking it apart. Figuring out how it does what it does. Like I said, I graduated here in 1987. Just so you know, I've been out of this now for 25, or out of what you guys are doing for 25 years now. I graduated in 1987, but I can tell you with a straight face that my first experience in reverse engineering happened about 20 or so years before that, when I was about 4 or 5 years old. My grandmother had a nice cuckoo clock, one that came directly from Germany. And I was just fascinated with this stupid cuckoo clock, how the fact that every hour this little bird would come popping out, making all sorts of noise. So at about 5 or 6 years old, I took it upon myself to reverse engineer my grandmother's cuckoo clock. It's still in a box to this day, the clock, not my grandmother. Yeah, I gutted that cuckoo clock into about 6,000 little pieces, and it has stayed in 6,000 little pieces ever since. And I have no idea how a cuckoo clock runs. But that's what engineers do. We oftentimes in reverse engineering, we take something apart, understand its workings, understand how it's doing what it's doing, and in the process of doing that, oftentimes we see ways to improve that process, and therefore we take upon ourselves the improvement. For us today, we're going to talk about reverse engineering of the human brain. And the human brain, folks, and I'm going to go through a series of slides with you, just kind of talking about the brain. And what I really want to do is I want to kind of give you a sense of what have we learned over the years about the brain, some of the remarkable things that it does. But very, very importantly, I want you to see as we talk about these things how none of these innovations are possible at all without some pretty straightforward engineering, some engineering contributions that make it possible for us to decipher some of these mysteries of the human brain being the most marvelous, the most mysterious system. And it is a system that we've ever encountered. It is an unparalleled, it is a unique control system. The fact that I'm standing up before you today and spitting this stuff out at you right now. Folks, yes, I've got bullets up here, but having bullets is one thing. Being able to stand up here and have all these billions and billions of synapses firing away and getting maybe 50% of it right as I tell you this is an absolute miracle as we go through this. It's a remarkable thing. It is for us as we think about the brain. What is it? Yes, it's an organ, we know that, but at the end of the day, it is an electrical and it is a chemical machine. And when we start thinking of it that way, and we start thinking in terms of, okay, let's understand the electrical aspects of it, let's understand the chemical aspects of it, that's when we can start pulling apart and understanding, well, what exactly does it do? And it is, and this last bullet I think is so important, it's infinitely adaptable, more powerful than any computer ever on the planet. It is unbelievable and unstatable, really, what all this thing can do for us. We've known about it, of course, for centuries. Yet, folks, it's really important that you understand. And by the way, I want to say too, there's a lot of things that are said about the human brain that are total BS. You guys have all heard things like, for example, why we only use 5% of our brains. Why, that's bull. That's not even true at all. That's just an old myth. It's an old wives' tale. But yet, to this day, we absolutely know very, very little about what this thing does. Starting to get glimpses. We have a fair idea of what it does. We yet know almost nothing about how it does it. And we even know less about its function too when something goes wrong, when something doesn't work right. What went wrong? Is it a chemical imbalance? Is it an electrical problem? What's happening here? What are the effects going to be? And of course we know, I know we all know some of the effects that can happen when the brain goes wrong. But the question becomes, what about subtle things? What about things that we never even thought there was a connection there before? How do we decipher what's not working right in the brain and then turn that around as engineers, turn that around into a problem that we can perhaps solve and improve the human condition? Well, that's what this is all about. This is what, as we think about reverse engineering the human brain, when we can break down how it works and understand how it functions, then we've got a chance, and this is an important thing, it's an important aspect of all engineering. You can't work a problem until you understand the fundamentals of that problem. You've got to know the fundamentals. As you guys go through your coursework in the next few years, you're going to be hit with things. You're going to be hit with a lot of things, a lot of very important knowledge. Every textbook you'll ever have is going to have just tons and tons of knowledge in it. But I want to give you a little piece of advice, and I think it's an important piece of advice for all of you. Always look for the fundamentals. It is the fundamentals that when you understand those things, those basic concepts, when you understand those will enlighten you on all the more hardcore stuff that you're going to learn as you go along. If you don't have a basis in the fundamentals, it doesn't matter what you know about the rest of the stuff. So when it comes to reverse engineering the brain, when we understand the fundamentals of it and what it does and how it works, then we can start unraveling, well, what's wrong, and in my specific area of interest, what goes on when it's involved in disease. Let's talk about disease. Aristotle, we've all heard of Aristotle, and this goes back to some of the earliest thinkings and earliest understandings about the brain. Now, Aristotle, reasonably sharp fellow, believed that the brain was nothing more than a cooling mechanism for our blood. It had nothing to do with not only disease, but nothing to do with how we thought or anything else. Aristotle actually thought the brain was pretty much a radiator for cooling off the blood. Fortunately, he got a few other things right. Now today, let's go fast forward in today. There are physicians and neuroscientists out here that probably have let the pendulum swing a little too far to the other side here, and there are people out there that believe that just about 3/4 of all the medical conditions that we can think up or know about are some way linked to the brain. And there's a lot of cases in medicine where you'll see linkages made to the brain where sometimes medicine and sometimes neuroscience or along those branches of science tend to want to write things off. When we don't understand something, it's really easy to say, well, that's all in that patient's head, and therefore it's not real. You don't want to be there either. The reality is probably the brain's role in disease is somewhere in between what Aristotle believed and what some of the overdoing it physicians are believing right now. But the question becomes for us folks, how do we know? How are we going to figure this out? How is it that we're going to determine what's true, what's not, about what the brain does and what its involvement is when we are dealing with specific diseases? It is in engineering, and this is the key of what I want to hit here this afternoon. It's in engineering that we, as engineers, have an opportunity to provide the tools that can be used, whether it's in an engineering field, whether it's in neuroscience, medicine, whatever, the tools that can be used for deciphering the function of the brain. So let's talk a little bit about some of this stuff. I want to talk about tools out there for reverse engineering the brain. Back in 1924, we're pushing what, 88, 90 years now. Back in 1924, the electroencephalogram, the EEG, was first discovered. And if you're not familiar with what EEG is a measure of the brain's electrical activity. It's usually measured, and I say usually because it can be done invasively, but it's generally done non-invasively by putting a whole bunch of leads all over your scalp and measuring the very, very remarkably tiny electrical potentials at the scalp, which are representative of the cortical activity that's going on directly underneath and in the neighborhood of those electrical scalp electrodes. Here's an example of some poor college student who apparently had his professor line him up and coat his head with all these electrodes and have a picture of what it looks like to have an EEG done. He looks thrilled, obviously. Interesting thing though, the scientist who figured out EEG in 1924 didn't publish it, didn't talk about it for 5 years because he couldn't believe what he was seeing. What he was seeing and making these measurements look kind of like this. Think of all these electrodes here as making measurements of the electricity up on our scalp, right? And so he's seeing just these tiny little squiggly lines. He wasn't sure if what he was seeing was just electrical noise, maybe something wrong with his instrument, or whether or not it had meaning. So for 5 years, this person sits on this and doesn't think that this is necessarily important, necessarily true. But that was 88 years ago. And of course, even after 1929, science, medical science and neuroscience knew that there was something important here, but it was very limited in what it could do in terms of understanding it. Because still at the end of the day, it's a bunch of squiggly lines. What do they mean? Now, in certain medical conditions, they can be very telltale. So for example, if a person has an episode of a seizure, well, you can see that in the electroencephalogram, instead of being these tiny little squiggly lines, you might all of a sudden have some larger activity. That's seizure activity, and that's indicative of what's going on and also specifically where in the brain. But fast forward to where we're at today. Along came computing technologies. Back in the 1980s, very specifically, computing technologies came along, and all of a sudden that, and a lot of great work that's been done in the mathematical field, suddenly that revolutionizes EEG science. We started taking those squiggly lines and breaking them down, doing things with them. For example, mathematically analyzing those, breaking those, for example, into their spectral components. And for those of you that are double E's, you'll learn in the next few years about Fourier theory and the importance of that, and breaking down signals like this and making something out of them, something understandable out of them. Today, with computing technologies, we're able to graphically represent that brain activity, not only what it is, but what certain subsets of the types of activity that it is, and also, very importantly, where it is. We can do things like statistical comparisons between disease groups and folks who are healthy, normal individuals, and make those comparisons mathematically and say, okay, well, here's an indicator that this person may fit more into a normal type profile, or a person who doesn't fit into a normal type profile. We're even able to do things today with computing technologies such as what we call inverse EEG, where in using inverse EEG, and think back to that picture of that guy that had all those electrodes all over his head. In inverse EEG, you're taking all those measures of all that electrical activity and then working the problem backwards to figure out, well, what brain centers must have been active to generate that electrical signal. So in inverse EEG, you're not measuring how much is there, you're measuring how much is there and where did it come from. And that's a really, if you think about it mathematically, that's a very remarkable thing. From that, though, and moving deeper into where we're at today, now neuroimaging is born. And neuroimaging is a very relatively young field out there. It's all about other technologies for visualizing brain function. And the people that have been behind these technologies, they're engineers. This is what we do. We are the scientists, we're the folks that figure these things out and reduce them to practice and make them something doable. For example, I'm sure everybody in here has heard of MRIs, magnetic resonance imaging technologies. Well, what's emerging and becoming rather, I wouldn't say common, but becoming less uncommon in neuroscience is something called functional magnetic resonating. In that case, the functional magnetic resonance imaging, or fMRI, measures and locates brain activity by detecting, in some cases, extremely minute and very localized changes in the flow of blood. Now, you may initially think, well, so? Well, the flow of blood is also indicative of what kind of metabolism is taking place in the brain, so that tells us what parts of the brain are actually working when something happens to us, or not working when something is not going the way that it should. So fMRI is a tool that's becoming extremely powerful and extremely useful for figuring out very, very subtle things that are wrong in the brain and in neuroscience. Here's a couple of examples for you, folks. Here's an fMRI image. The red spots you see all over that are superimposed on this brain image here are indicators of what part of the brain are actually metabolizing or using metabolites during a process. What you see over here on the left is what happens when a person sees an avatar, an image of a face. Make a comparison here, though, to what you see on the right-hand side, and these are the portions of the brain that actually light up when, instead of seeing a representation of a face, you're actually seeing the face itself. So this shows us, using fMRI, that the brain actually responds differently when you're actually looking directly at somebody versus representation of that somebody. Kind of neat. Now here's one over here. Here's an fMRI image showing brain regions suppressed by alcohol intake, includes visual, motor, feedback centers, which is fancy brain language for the parts of our brain that connect what we see to what we do. So as you can see right here in this image, using fMRI, when somebody's under the influence of alcohol, we see that the portions of the brain that are supposed to make our hands do what our eyes and our mind are supposedly seeing and thinking, they don't work so well together. So I figured I'd throw that one in there, realizing, with all you incoming freshmen, that might be some handy information in the next, few years for you to be aware of this. Shouldn't be, by the way. Here's some other stuff. Positron emission tomography, PET. imaging. Left-hand side here of this, you see PET imaging showing some areas of the brain that are diseased in Alzheimer's disease. Notably here, the red images that we see back here in the occipital areas of the brain. Interestingly, over here on the right-hand side, these are those inverse EEG images I was telling you about. Remember I said that in inverse EEG, we're able to actually figure out what parts of the brain aberrant cortical activity comes from. In this case, the red that you see right here is literally matching up using inverse EEG to what we're seeing on PET tomography. Over here, here's another, this is another fMRI image of differences between healthy normal controls and folks with attention deficit disorder. So we'll be discovering that in most of you in the next few years as well. And we'll be able to see it with fMRI. Here's one that I'll just drop your jaw. This is SPECT imaging here, folks. Now, SPECT imaging is not a very popular type of imaging, but it's also out there as well. It's single photon emission computed tomography. What you see in SPECT imaging, though, SPECT goes out and takes a look at perfusion of blood as well. It's interesting, and I love this image. This is what we see in SPECT imaging with a healthy brain. We see blood flowing and operating all over the place. Compare that to the brain, well, that is a brain, by the way, over here on the right-hand side of an individual who has an opiate dependency. And in this particular case, that might be somebody, for example, who's dealing with a chronic pain illness and might have to take opiates to manage that pain. What's really remarkable here is check out the difference in the blood flow in the brain of the individual with opiate dependencies compared to the healthy normal. What you see here, folks, these are just holes. All right. When you're looking through that, if you happen to see some daylight or dark in this particular case through that, these are holes that are representative of areas of the brain that are actually not perfusing blood the way that they normally would. So the drug in this particular case is literally shutting off flow of normal blood flow to the brain. And we see that using SPECT imaging by seeing voids in where the blood is actually being taken up. Yeah, there's some good ones out there on smoking. As a matter of fact, if anybody's interested, Professor Torfey asks a good question. I want to make sure everybody hears it. What about smoking? If you're interested, it's really easy online to just do you can do like a Google image search, for example. Just type in SPECT and things like smoking or alcohol, drug addiction, you name it. And there's just all sorts of remarkable pictures of what the person's brain looks like when they're under the influence, let's say, of these kinds of intoxicants. It's really something else. Now, yes, where? Oh yeah, hi.
Are like those holes on the brain, are they permanent from it?
That's a great question, and I want to make sure everybody heard it. So the question over here was, well, what about those holes? Are they permanent when that happens? The thinking is it's not necessarily. It depends upon the disease itself. So in certain types of disease conditions where you might have something that's, it's refractory to any kind of treatments or medications, then you might expect to see something permanent like that. But like, for example, that thing I showed you of the areas of the visual motor areas and alcohol use that kind of shut down, that's going to go away and once you sober up. That's what it boils down to. So yes and no. Good question. And these questions, by the way, these are great. If you have questions, fire away. Don't hesitate. It's good to get them out and answer them right now. So my area of interest specifically, and Dr. Tabacoli brought it up, my area of interest is I've become rather involved in understanding and ostensibly defeating the brain's role in chronic pain diseases. And I want to talk to you a little bit about chronic pain because it's one of those things, especially at your age, most of you are not really, hopefully not overly influenced or bothered by these kinds of things. But you have to understand that as you age and deal with an aging, like in my case, my parents are still alive, and so, as you deal with older people, you start realizing, hey, chronic pain's a big deal. As a matter of fact, we didn't know how much of a big deal it was until just a couple of years ago when the National Academy of Sciences Institutes of Medicine actually did a 2-year study and took a look at, well, how much does chronic pain really affect people in the United States? And then some of the numbers were rather astounding. As a matter of fact, I do want in disclosure say that some of the numbers are actually somewhat disputed because they're really so excessive, but it's a big problem no matter how you slice this up. The IOM's report says, or claimed, that chronic pain in just the United States alone affects as many as 116 million people in this country alone. And of course, it's a worldwide global healthcare crisis. So by me talking about the United States alone, I'm not saying that this is just a problem we have. This is a global issue here, folks. In the United States alone, the IOM report indicated or showed that the annual impact on our healthcare system, the annual healthcare cost, including what people pay out of pocket to deal with their pain conditions, runs somewhere around about $565 to $630 billion every year. People are paying and healthcare systems are burdened by these problems over and over again. There's nothing that's mitigating this problem. As a matter of fact, the 2010 IOM report, its main conclusion was the fact that still today, where we are in medicine, assessing and very importantly, treating chronic pain is still a problem. It's a difficult thing to fix. When a person has a chronic pain condition, like let's say back pain or chronic headaches or something like that, or chronic arthritic pain, those kinds of things, medicines that are out there, treatment approaches that are out there just aren't getting the jobs done. As a matter of fact, current medications for chronic pain conditions typically, unfortunately, yield pretty poor treatment outcomes. In other words, once you got chronic pain, the likelihood is you're going to be in it for a good long time. Question then, why? What are we missing? What have we not understood? What have we not figured out when it comes to treating pain? Here's a fact for you folks. If I don't know, wander around here and blah, 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 and I trip and I bump my knee on this, my knee is going to become inflamed. It's going to hurt. What am I going to do about that? Well, I'm not going to go too nuts. I'm going to go out and get some Motrin or something, take some NSAIDs, standard of care treatment, and guess what's going to happen? It'll stop hurting pretty well. That'll control it quite well. But if it works in that kind of a case, why is it when somebody hurts all the time, those medicines don't do the job? What did we not see? What did we not get? That's the question for us. Well, it is very, very specifically because of the work and the capability that has been brought to medicine and to neuroscience through neuroimaging technologies that we're starting to understand that there's yet a new paradigm in pain that up until about 25, 30 years ago, we didn't even know this existed. And it's what I call the centralized pain or CP paradigm. Centralized pain, folks, this is what happens to us when pain causes, and by pain causes I mean pain that's existent in our periphery, like the bad back or the hurt knee or something like that, when over time those things don't resolve and they end up causing an alteration in neural network functionality within our central nervous system and very specifically within our brain. What happens is suddenly, and to put it as simply as I possibly can, our brains over time become hardwired to essentially think that everything is painful. And what we're starting to understand about that is, well, this centralized, and when that happens, by the way, we say that that pain has become centralized. When that happens, it's no longer what's going on out in the periphery. The fact that I've got a bad knee from falling down over there, that's not what's causing me pain. It's the fact that my brain thinks that it's causing me pain, and in centralized pain, we feel that pain as though it actually exists, as though there's something really wrong there. Take, for example, people with knee osteoarthritis. Knee osteoarthritis is a big issue, and it's going to be a bigger issue in years to come as our general population ages, and as our general population kind of gets a little bit bigger and bigger over time. Knees go bad. Standard of care in knee osteoarthritis, it's medicines, and by the way, the medicines generally don't work. As a matter of fact, one of the ways we have for measuring how well a medicine works compared to a placebo, a sugar pill, is we look at where do patients put a little mark on what we call a visual analog scale. It's 100 millimeters long. One side's like absolutely no pain, the other side's like the most pain you can imagine. And we ask patients to put a mark there, like where's your pain on that scale? Check this out. The difference between standard of care for medicines used for treating osteoarthritis and a placebo is only 4 millimeters difference on a 100 millimeter visual analog scale. What does that tell us? It tells us that there's really effectively no difference between just handing somebody a sugar pill and saying, here, this ought to do the job. If that doesn't work over time, we take a look at things like, for example, total knee replacements, very expensive surgery. But yet people that go through a total knee replacement, over time, we find that about 40% of them after 2 years after surgery still have the same pain. It didn't correct anything. Even more bizarre yet, there are cases, lots of cases in clinic, where you'll see somebody come in, for example, with one knee that's damaged, that's arthritic. And we know when the knee is arthritic, if you reach down and palpate, if you move the knee around, that's going to generate a response. That's going to cause pain, right? You'll have a patient who will have a bad arthritic knee, the other knee is perfectly healthy, and over time what you'll find is even when you palpate the healthy knee, they feel the exact same pain as they would feel if you're palpating the bad knee. Why? What's wrong with a healthy knee? Nothing. Nothing at all. Yet that pain is centralized. Now all of a sudden there's an imprint, there's a hard wire in the brain that it has centralized that pain. And when that happens, you get a reduced pain threshold. Things that, for example, shouldn't have made you hurt before, do that all day long. Doesn't hurt me one bit. I've seen patients in clinic that have centralized pain that if you do this, they will scream. I don't mean say ouch. I mean scream. Because what shouldn't cause pain does cause pain due to this reduced pain threshold. They have heightened response to minimal stimulus, and frankly, a lot of times just spontaneous pain. They just feel pain all the time, and there's nothing going on. There's nothing in the periphery that's causing pain. This is what centralized pain is, and we're just figuring this out because neuroimaging showed us what it looks like. There's been some great work that's been done. These pictures down here show it. This is an fMRI image here, functional magnetic resonance imaging. We talked about that earlier on, but this is showing very specifically centralized pain, the parts of the brain that are over-responsive in the chronic pain condition fibromyalgia. And if you're not familiar with fibromyalgia, this is a chronic pain condition where your whole body, for no reason whatsoever, just starts hurting. And there's nothing wrong in the periphery. Yeah, you'll hurt the rest of your life, and there are very few medicines that do anything about it. Hurts a lot, and we know now. As a matter of fact, 10 years ago when medical science talked about this disease, that's one of those where doctors were more than happy usually to kind of shrug it off and say, it's all in their heads, we don't know why. Yeah, we know exactly why now, and we know exactly what causes it. We are working on how to fix it. You see this here in the fMRI image. See these yellow segments right down here? That just happens to be in a part of the brain called the somatosensory cortex. That's a part of the brain that just happens to process all the inputs that come in from the periphery. And as you can see, it's lit up like a Christmas tree. It's that part of the brain that takes any input from outside like this and makes it a big, big, big deal and says to the pain processing centers in the brain, wow, did that ever hurt? And we actually feel that hurt. We see exactly the same thing using inverse EEG. As a matter of fact, the red spots you see up here, this is inverse EEG imaging showing the exact same problems, exact same areas, the somatosensory cortex. I mentioned osteoarthritis a few minutes ago. Just in the last few years, we're starting to figure out using fMRI imaging that problem that I was telling you about, where people have long-term osteoarthritis and all of a sudden they start hurting in places where there's nothing wrong. We're seeing the exact same patterns, and in some cases the exact same areas showing centralized pain in that case. So this centralized pain paradigm in chronic pain is becoming a big deal. It's revealing to us what's really going on here. So we go back then to the question of, so what? So, okay, we see these nice pictures where there's all these nice red and yellow blobs all lit up. So what does it mean? And most importantly, what are we going to do about this? How do we fix this problem? I mean, we can take people with centralized pain and we can medicate them all day long and it doesn't help. So what might help? What can we do? Well, we had to dig deeper. We had to understand even more. Pictures are nice. Little yellow dots all over pictures are wonderful. But we had to understand, well, what exactly is going on? Work in that area falls into the category of, and this is one of my areas of interest, brain network connectivity. Brain network connectivity is the relationship between the areas of the brain that are functioning, that are actually doing and responding to things coming in from the periphery. We know, and this picture here is kind of just meant to be a nice looking graphic representation of, okay, we know that when something happens, our brain responds, it lights up, right? What we're learning, though, is that when one part of the brain senses something, then not only does it respond to that, but it talks to other parts of the brain that are responsible or at least involved in ways we respond. It's called brain network connectivity. A really simple representation is what you see here in the image, where we see, for example, the portion here that's flashing, the blinking dot that you see right here. The idea in brain network connectivity is when something is sensed in the brain, it communicates that information to other parts of the brain so that the other parts of the brain will receive that information and, very importantly here, folks, properly respond to it. In network connectivity, and this goes back to the unraveling, the reverse engineering of the brain here. What we're learning right now, learning today in chronic pain, is these network connections that you're seeing, particularly in areas where the brain responds to peripheral inputs and then communicates that to pain processing areas. It turns out that those network connections are really wired up. It's not just a few connections. Those dots are connected kind of like what you see right here. In centralized pain, we have far too many network connections in the areas between processing and response, especially to painful inputs. So we get them back to one more time so we know about it now. We get it. Centralized pain. This is so simple, folks. Centralized pain is nothing more than like turning up the volume on the control. It's like turning up the volume on an amp. We all know what happens when we turn the volume up on our amps, radios, whatever. We get more sound, more out of it, right? Centralized pain is nothing more than akin to turning up the volume on our pain processor. It cranks it up. The question then is, what are we going to do about it? Well, my area of research, what Dr. Tabacoli alluded to, is I've been working now for a number of years in the area of neuromodulation. Now, neuromodulation is a device-based form of therapeutic. It's not a medicine-based form of therapeutic. In neuromodulation, we use device technologies, particularly electrical, in some cases repetitive magnetic field type technologies, but I only work in electrical, just so you know, to use non-invasive electrical signals that can actually pass through the outer tissues, pass through the skin, the skull, the portions of the types of tissues that don't conduct signals through them as well. We're working on how do we actually modulate signals in a way that we can pass these signals through those tissues and use those signals once inside the cortex to actually break down and normalize these abnormal network connections. And then of course the question becomes, if we can do that, if we can get in and actually change that abnormal network connectivity, what's the result? What happens to patients when we do that? And of course there's always questions of, is it safe, that kind of thing. So that's what I've been working on. As a matter of fact, I'm already past this bullet right here, but I mentioned the technology challenges of getting the therapy signal past the outer tissues. Let's face it, skull, skin, they don't like to conduct electricity very well at all unless you really, crank it up. But very importantly, how do we get it in from the outside and target specific cortical tissues? Now, as Dr. Tabacoli mentioned, some of my entrepreneurial work, I'm actually working with a group of people that have been developing these procedures and processes, and actually a medical device to work on this for a number of years right now. I'll tell you that the technique has already been tested in a human clinical study. We tested actually a number of years ago on 77 patients with the chronic pain condition fibromyalgia. And I want to point out to you that, again, fibromyalgia, even though there are now currently 3 drugs that are approved by the FDA, the overall clinical outcomes with these drugs are really way below what they need to be, so we generally don't get good results with these patients. But when we use the neuromodulation paradigm on these folks, it turned out that we had a very, very good result. As a matter of fact, these patients, on the whole, not only got better at the end of study, but we're now looking at these patients about 4 years post-therapy, and we're finding that the therapy improvement, or the symptom improvements that they had at the end of the study are still there 4 years later, and they're not taking medicines. So the question becomes, okay, is that a fluke? What exactly did you guys do here, and why are they better and staying better? Because that's something that in the chronic pain field, especially in fibromyalgia, is completely unheard of. It just doesn't happen. Well, we think we know why. It goes back to, again, the central pain paradigm. The image that you see up here is the image that you saw a few minutes ago. It's the same inverse EEG image, and remember the red areas up here show us the areas in the somatosensory cortex that are important, we think, in terms of the centralization of pain in these patients that are actually functioning abnormally. This is the area of the brain that's not working, where the network connections are too much and causing them to be over-responsive to pain. This particular image that you see right here is a very typical representation. We saw this exact same thing in just about all of these patients. This particular one you see right here, just to give you an idea, this is an individual, this is a patient who was at the time about 41 years old. She had been dealing with this condition for 12 years, had tried literally every medicine imaginable to try to get over her pain. And again, when I talk about pain that was so bad she had a hard time just moving, it hurt so much. Had been 12 years with no successful treatment whatsoever, and so she was one of the 77 that went through the clinical study in this particular case, testing this paradigm out. Here's what she looked like after treatment. The red's all gone. The red was completely gone in this particular case. The abnormality that's associated with centralized pain was gone. We're back to here, just a perfectly normal brain. Both the centralized pain abnormality and, very importantly, all of her symptoms completely resolved. She's now post 5 years, or actually 5 years post-therapy, and is perfectly normal. So the question becomes, okay, did we get it? Did we actually resolve the abnormal network connectivity that's associated with her symptoms in this case and the symptoms of so many of these other patients here? And what exactly does this mean? Well, this is the problem at hand. This is the reverse engineering that needs to be going on, not only the reverse engineering, but the forward engineering as well. We know something's happening here. We know that we've got patients that got better. We know that, okay, thank you, Dr. Tavicoli. I know that I'm going on too long now. We know, but we know that symptomatically improvements took place and they're lasting, but we got a lot of work to do to understand why, because once we understand why, we can then carry it to the next level. Can we repeat this over and over again? I want to show you a couple of things here, and these are just my last two slides. I told you earlier on that this is all about, we think all about network connectivity, right? In network connectivity, we can measure it a number of ways, and it goes all back again to neuroimaging or EEG imaging. There's just all sorts of ways for us to do it. And again, thanks to the engineers. The engineers figured these things out and made these things practical, and that's very important for all of you, budding young engineers to know about here. But we took a look at the patients in the clinical study, and just so you know, half of the patients in the study actually, when they were treated, were given a sham. They weren't given anything at all. They thought they were getting something. They weren't. But we took a look at those folks and we looked at measures of their network connectivity before the therapy intervention, and then we looked at it again after the therapy intervention, about 12 weeks later. And we looked then for differences. Were there differences in their network connectivity? Because the differences in network connectivity, of course, might map to why their symptoms get better, right? So now these are the people that took the sham therapy. And when we looked at the differences, there were only a couple of connections. And I want to point out too, folks, there are 19 different places, and this is using an EEG technique. There were 19 different places where we placed electrical surface electrodes for measuring the EEG. As you see here, a couple of different connections actually did show some significant improvement. By the way, when you got 19 connections, if you work the math out, that means you got 171 different possible networks you're measuring here. So a little bit of change in the folks that had the sham treatment. The P less than 0.001 over there is a statistical indicator of the probability that that wasn't by chance. So the probability here that this was a chance occurrence was pretty small. Actually, it was even smaller yet in the two red bars that you see. Now, you might look at this and say, well, gee, then, why did the people that were just getting a sham treatment, why did they have any changes in network connectivity? Very simple. Our networks have changed a lot since we started this. Okay, our networks are constantly changing. You take anybody into a clinical setting and sit them down and just have them kick back and relax for 20 minutes, you're going to see network changes. Okay, so we expect to see a little bit of change in the sham group. But it was the treatment group that gets kind of exciting. The people that actually took the neuromodulation therapy, when we looked at their changes in their network connectivity, we saw this, and then we saw that, and looking at the even more significant changes. So these networks, and these are all reductions in abnormally high networks that we think are associated with chronic pain. As you can see here, the yellow bars and the red bars tell us that in people that were treated, there actually was a measurable, in the entire group, a measurable change in that network connectivity. And the clinical data that's emerging now is suggesting to us that once you change it, it lasts. And that's actually for people suffering from chronic pain conditions may be some really, really good news. It's a promising advance. We're seeing promising advances in treating chronic pain, and it is entirely, folks, entirely thanks to work that's been going on now for decades to reverse engineer the brain. Thanks.